much for the invitation. I'm really excited to be here. It's been a little while since I was in Alpine, so I'm really happy to be here again. And I'm an associate professor at the University of Texas in El Paso. I've been there for 11 years, and I really like El Paso and the West Texas region and southern New Mexico. So it's an area I appreciate very much. And I wanted to mention also that I have a mix of different projects going on. So I do some work in tectonics and using seismology, seismic imaging to look at tectonics. I also do some work on earthquakes. I also do some work on water systems. Half of my 5 PhD and master's students right now are working on water-related projects in West Texas. So all of these are big interests of mine, and I'd be happy to talk more with anyone the rest of the day and at the happy hour tonight. And I'll be talking about, so in this presentation, I'll be giving some general introduction to just a few different geophysical methods that can be helpful for hydrology and hydrogeology questions. And some of this work is funded by NSF, Army Research Lab, and also the Institute for Strategic and Sustainable Resources at UTEP. Seems like it's, sorry, just trying to, it was working earlier. Okay, there we go. Okay, so I decided today to talk about just 3 geophysical methods. So I'll be talking about electrical resistivity, gravity, and seismic imaging. Then I'll talk a little bit at the end about particular future opportunities and challenges and have time for questions. But before talking about some of these methods, I wanted to give a sort of a hydrogeology introduction, especially to the Hueco and Mesilla bosons, which are in the El Paso area. Also, one of the projects I'll talk about is also in the Jornada del Muerte Basin in southern New Mexico. And I should mention that at UTEP, we have a number of people working on water issues, including Mark Engel and Lynn Ma and Hugo Gutierrez. Those are some of the faculty involved, and each of them has a number of students involved. So they're all very interested in this region and hydrogeology. And so I'm sure they'd be happy to talk to anyone about various issues. And we've already heard some general overview about the aquifers of Texas and West Texas, so I won't spend much time on this. But this is a map of the principal aquifers of the US by the USGS. And I thought it was interesting that they grouped together sort of a very large section as one system. Of course, we've seen a lot more detail in that system today. So that's most of the aquifer system I'll talk about in the introductory part is the Rio Grande aquifer system. And here's a map of the Texas aquifers, and we've already seen this. So again, I won't spend too much time on it. But again, I'll mostly talk about the sort of purple Hueco Mesilla boson aquifer in far West Texas. And this area is part, of course, again, I'm sort of talking about some things that have already been covered. So, but just to talk a little bit about it. So this is part of the Rio Grande system, of course, and just a few other statistics in addition to what we've seen already. It's the 5th longest river in the US. I'll be mostly looking at kind of the middle to lower Rio Grande region, thinking about El Paso and the far West Texas area. This is, of course, a semi-arid climate with limited freshwater resources. There's the precipitation per year is only 25 centimeters per year. And evapotranspiration is more than 200 centimeters per year. And there's in the El Paso area, El Paso Juarez area, there's over 200 million people living there. So it's a big concern, where the water is coming from. And it was great to hear about that today. And just a few other comments. So the agriculture water use is mostly from, 90% of it in the past has been from the Rio Grande, with 10% from regional groundwater. And then the municipal water use, however, is mostly dominated by the groundwater, as you heard from El Paso Water earlier. And so thinking about this system, some of the human impacts on the hydrology of the area and the water flows include things like reservoirs, dams. We've seen this in a lot of detail already, so I won't spend much time on it. There's networks of irrigation canals and drains as well. So you can see some of these here, the alluvial basins are highlighted in brown, irrigation areas. And just a few elements of this system. So 193,000 acres of agricultural lands are along the Rio Grande in New Mexico and West Texas. And you all may know, but I think it's the largest or second largest pecan growing area in North America. But basically it has a large amount of agriculture, important agriculture going on in that region. And the average normal release of water is about 790,000 acre feet per year, with 60,000 acre feet per year to Mexico. And the 900 million meters cubed of water per year is from the Rio Grande for this. So the, and then, sorry, 490 million meters cubed of water is withdrawn from the regional aquifers for water use in the cities. So these are just like some other statistics about water use in the far West Texas region and along the Rio Grande. As you all know, and we've talked about already, a lot of the region has challenges with salinity in the water. And so this is thinking about the Rio Grande water. And you can see here this work from out of University of Tennessee by Anya Sienkiewicz, who's looked at salinity along the Rio Grande River. So you can see upstream at near Taos, the TDS and the electrical conductivity of the water, Elephant Butte Reservoir, downstream Rio Grande, it's more higher TDS and higher electrical conductivity. And then in the El Paso area, this agricultural drain has higher still TDS and electrical conductivity. And so those are measuring the salinity, and the salinity tends to be more than 2,000 milligrams per liter the TDS tends to be more than 2,000 in the regional aquifers, as we've also heard earlier today. And so this salinity has high impacts in terms of the irrigation with the high salinity waters. You can see in the pecan orchards where they're doing flood irrigation, a lot of salt deposits at the surface. The first slide I had an electrical resistivity survey, actually we did last Monday with my geophysics class in a pecan orchard in Tornillo. You can see the salt deposits on these, where they're doing the flood irrigation. And this process has led to significant salt loading in the soils, and that's reduced the crop productivity. So it's a big concern for the farmers and the folks that work in agricultural areas. And so there's been a wide variety of studies looking at the sources and the impacts of the salinity. I've listed a number of those here. There's been geochemistry and hydrology and isotope studies and remote sensing studies looking at this. And it's an ongoing area of research. I know for example, in the pecan orchards, and again, some of you may have direct experience with this as well in this region, but in Tornillo, there's sort of clear patterns that show that where the soil is more saline and you have higher clay contents as well, you get smaller trees with lower productivity for pecans. So that's a kind of a big concern for the farmers, is how to avoid having problems with growing their pecans. And again, thinking of salinity, so evaporation alone can't account for increases that we've seen in total salinity. So here's some of the different processes that may be influencing it according to some of those different papers that you saw in the previous slide, and some of them are also repeated here. But processes like solutes released from chemical weathering, upwelling of deep saline groundwater, sort of shown here in this cartoon, displacement of shallow groundwater by irrigation water and extensive use of fertilizers is shown here. And then waste effluents becoming major tributaries to the Rio Grande is also a contributing factor. And here's some of the, basically, again, I'm not a geochemist, but this is from one of my colleagues. So looking at the sulfate to chlorine ratio for different municipalities along the Rio Grande. So you can see El Paso here, Las Cruces, Red River, these are northern New Mexico, Jemez River, Bernalillo, near Albuquerque. And so you can see the sulfate to chloride ratio in the Rio Grande is in blue. Some of the tributaries are shown in red. These are water samples. And then the wastewater treatment effluent is shown as yellow stars. So you can see, like we've heard earlier, that the wastewater going back into the system in El Paso is basically the same chemistry as the Rio Grande water. And downstream, we see an increasing contribution of groundwater as well. And so again, just kind of zooming more on the West Texas area, here's a more detailed look at some of the aquifers. And I just wanted to mention, I'll show data later on from the Jornada del Muerte about this purple, and also from the Hueco Bolson, which we've already heard about. I think I'll probably skip over this. We've heard a lot about different aquifers. These are sort of just a compilation of statistics for aquifers around El Paso. So Jornada del Muerte, looking at surface drainage, groundwater storage, annual recharge, the climate, aquifer types, aquifer materials. And just wanted to highlight that these are some of the important elements that we want to look at when we're looking at the different aquifers in different areas. And then here's a summary of some of the water uses around El Paso as well, and for these different basins that are around the El Paso area. And for the Mesilla and the Hueco Bolson, this is from Collins and Randy 2000. There's been a variety of other work since then, but this is still sort of provides a nice summary overview of the hydrogeologic framework of these basins. So we saw the beautiful Franklin Mountains earlier, kind of in the that cuts west and east El Paso from each other. And you can see here the general hydrogeologic structure of the Mesilla Bolson and the Hueco Bolson. And I'll show some data later on from the Hueco Bolson. I have 2 students doing some work there looking at the water systems. And I wanted to show these sort of hydrogeologic frameworks as a context so we're going to be talking about some different geophysical methods. And so one thing that I'm really interested in is using geophysics to map the subsurface. And so these types of models of the subsurface are, of course, benefit greatly from surface data and geology and hydrogeology, but can also benefit from different types of geophysics mapping the subsurface. And the final thing I wanted to mention in sort of the hydrogeologic background, we've heard this a little bit earlier today, was some of the processes for recharge in semi-arid basins. And 2 of the largest processes, or two processes that occur, are what's known as mountain block recharge and then mountain front recharge. And so you can see the area A where you have mountain block recharge in the mountains, and then mountain front recharge in area B. And these are, this cartoon is is showing you different ways that mountain systems in semi-arid basins can recharge. So you do get alluvial aquifer recharge, ephemeral channel recharge, diffuse recharge in a typical system. I've heard data that in the El Paso region, at least, it seems that the aquifers are not being recharged at all by these by natural sort of mountain front recharge and mountain block recharge, because there's just not enough water going into the system to make a difference. At least it hasn't been documented with science, as far as I know, recently. If someone knows something different, please let me know. That's what I've been told by my hydrogeology colleagues. And but these processes in general are a significant component of recharge, and so potentially allowing the systems to recover or finding ways to make. In El Paso, it may also be some of the waterways are may move water into places that don't allow it to actually recharge. So there's a lot of sort of concrete pathways and things for water in some areas. But as we heard earlier, there's projects to increase the ability of rainwater as well as the reused water to be going back into the aquifer, which is fantastic. And so the final slide I have kind of on the hydrogeologic background, just thinking of the mountain block and mountain front recharge. Again, you can see a different person's cartoon of the mountain block recharge, mountain front recharge zone, and where those different types of recharge are occurring. But then I wanted to kind of highlight sort of a little bit more. This is another cartoon a bit more detailed about kind of the fractures beneath the surface that can impact this. And you can see this limestone, active mudstone, sandstone, active systems where you have fracturing. and fluid going into the ground through fractures. Sometimes you can see small evidence at the surface that it's an area where you might have fractures that can allow water back into the ground, or where there might be a fault. And I wanted to show this because some of the, I have some seismic data that crosses over some kind of mountainous areas, like one of the Piedmont slopes of the San Andreas Mountains in southern New Mexico, where we're trying to look at where are the faults that might be recharging the system there. And so the next section, I'll be talking about a few different types of geophysical methods, and I'll talk a little bit about basically how the methods work, because I didn't know how much geophysics background might be here. So forgive me if you already are an expert in geophysics, but I just wanted to make sure to bring everybody along if some folks haven't had so much exposure to geophysics. But I wanted to mention, so to me, like the power of geophysics is really the power to sort of look beneath the subsurface and combine that with all of the surface data. Drilling data is so critical, but it gives you another type of data to look into the subsurface. And so this is just a cartoon showing, a drilling rig. If they drill like a deep well, don't find water, they might be like, they may not, you have some great data from that well. But if you could get like a bigger picture using other types of methods that look beneath the surface, it might help you to know that you could drill, a little ways away and you would hit your water system. And the type of geophysics that I'm talking about today is mostly considered part of either near surface or environmental geophysics. So these are some textbooks I like on the topics if you're interested in more. And I won't be able to talk about all the different types of geophysics. My class I mentioned where we did electrical resistivity last Monday with our lab is a non-seismic geophysics class. So we cover all the methods except seismic in that class. We have a different class that covers just seismology. But I wanted to kind of highlight the sort of suite of methods that exist. So there's methods. So the top of this slide is listing a number of geophysical methods that measure certain physical phenomena. And then the bottom part of the slide has the corresponding subsurface physical property that method measures. And so, for example, electrical resistivity imaging is measuring resistivity in the subsurface. Seismic refraction, or sending elastic waves into the subsurface, allows you to measure seismic wave velocity and density. And electromagnetic ground conductivity methods, you can measure conductance, inductance, and permittivity of your soils or your subsurface system. Ground penetrating radar, you measure dielectric properties of the subsurface through using electromagnetic waves. And then gravity measures basically as a way of measuring the density or the mass distribution in the subsurface. Mass per unit volume is density. And then magnetics allows you to measure magnetic susceptibility. And all of these methods can be used to image subsurface structure, to look at subsurface structure, and to constrain faults and different lithologies. And depending on your area and the depth that you want to look, that you might select different methods. And the one other just bit of background terminology is so people sometimes talk about passive geophysical methods and active geophysical methods. In passive methods, you're sort of listening or measuring the background level. So I'll talk about gravity today. That's an example of a passive method because we're measuring the Earth's gravitational field in a specific area. There's also active methods, and actually the other two methods I talk about today are both active methods where the scientist creates the source. So, like out in an oil field, you have a vibrator truck creating seismic sources, for example, or explosions or air guns in water. And then you measure those waves coming in. So that'd be considered like an active geophysical technique. And the electrical resistivity tomography that I'll show you later on is also an active technique because you put the electrical current in the ground and then measure the voltage that results, and you can get a measurement of the conductivity in the subsurface. For hydrology, these are some of there's a lot of ways you can use geophysics. These are just some of the typical ways that it's used. So you can use it to detect contaminants or different chemistries of your subsurface system, to map out groundwater, characterize groundwater flow and fractured rock, to track saltwater intrusions in porous media, or to do remedial work with the water supply to monitor the system. And this example from the bottom, this is a survey in Monterey in California. So this is a coastal region. And towards the bottom of the slide is basically the ocean. And so they did the survey along the beach in California, collecting electroresistivity data. And you can see here a couple of rivers feeding into the Monterey Bay area. And the electroresistivity data, basically, the blue is showing you higher resistivity or fresher water, and the red is lower resistivity, which is higher conductivity, and saltier water. And so you can use this basically to track if you have salt coming in from the ocean in this case into the inland aquifers. As one example, you can see that it's fresher near where the rivers are, as you'd expect. And there are certain areas where you have more, the red is the saltier water, where you have more salty water potentially intruding into the beach area and then possibly further inland. And I know in this region, they have challenges where if they pump too much of the inland aquifers, then the salt water from the ocean is sort of pulled in. And so you end up potentially having issues where your freshwater aquifers or your fresher water aquifers are mixed more with salty water when you're drawing down the aquifer. So they want to make sure to keep that balance and understand what's going on. So then I'll talk a little bit more about electrical resistivity, which was what was just shown in that example data. And there's a master's student at UTEP, Jose Cabral, who's mainly advised by Dr. Hugo Gutierrez and Lynn Ma. And he's working out in the Tornillo, Texas pecan orchard. So my class helped him set up this survey last Monday. So this is out in the pecan orchard, and you can see here these metal bars are the electrodes, and then you have a cable in between them that's connected to a computer that's powered by a generator, and then it sends electrical signal into the ground through these electrodes. And this method, and the goal of this project specifically, was to derive the water depth, to look at the aquifer structure, to look at lithology variations, and then also salinity, specifically in this area under the pecan orchard. And so we were aiming to look down about 50 meters in this area. And the water table, at least at this, tends to be about 3 meters, 3 to 4 meters, 10 feet. And so with electrical resistivity, the method basically measures the flow of current through the ground and the ability of the ground to hold charge. And so why would you want to do this? So different kinds of earth materials conduct electricity better and hold charge longer than others. And it can help you to work out where you might have different kinds of materials. And as you saw before, to work out where you have saltier water or less salty water, or saltier soil, less salty soil, that kind of thing. And here's just a couple other pictures of the same. These are different instruments for collecting electroresistivity data. This is showing you the computer system for the AGI Supersting that we have at UTEP. This is on our campus by the geology building. But there's this line of electrodes here, just like you saw in the pecan orchard. And then this was a survey I did probably 20 years ago almost, when I was, probably 15. When I was a postdoc in England, we had a geophysics field class that did some surveys at the beach there, but we just had 4 electrodes. We didn't have such a fancy system that we have at UTEP with 112 electrodes. But so things that affect resistivity are different rocks or other, I mentioned already, it's sort of whether or not the rocks conduct electricity better or hold charge longer. So you can see here the equation for resistivity, which is sometimes represented with rho, is the resistance times the area over the length. Resistivity typically has units of ohm meters and can be normalized. And the R is the same resistance you all might recognize from Ohm's law. So V equals Ri, voltage equals resistance times current. And as a note, so resistivity is the inverse of conductivity, which is sometimes represented with sigma. Conductivity has units of Siemens or millisiemens. And so you may see that in some of the data that I'll show you. It's either in conductivity or in resistivity. It might be in millisiemens or in ohm meters. And good conductors in the earth include ore mineral grains, fluids, clays, and saltwater. Resistivity of materials is extremely variable. It can depend on the fluids, the porosity, the grain size, and the fractures. And just as a note, since we're thinking about saltwater and freshwater, so salty water might have a resistivity of 0.1 to 1 ohm meter, whereas freshwater might be 10 to 100 ohm meters. And if you have frozen ground, it's even higher. I've been doing some work in the high Himalaya, looking at glaciers and water systems related to those. And we have permafrost there, as well as like ice cored moraines. And so what affects resistivity? So this plot is quite helpful in that it shows you resistivity on this axis. And then the corresponding, 1 over resistivity is conductivity. So corresponding conductivity down here. And you can see the typical, this is just kind of like what you'd find in a textbook, typical resistivity or conductivity values of common earth materials. And so I already mentioned a few, that like this freshwater versus saltwater. Saltwater is more conductive, more resistive compared to freshwater. You can also see clays. You could distinguish clays from tills, from sand, for example, and differences between different rock types as well. You may also notice that a lot of these are overlapping, and there's often more than one possible answer just from the geophysical data for all of these data types, for all of these methods. And so it's important to have as many types of data as possible, and especially surface data, drilling data, in order to ground truth some of the geophysics. And you might ask, well, how deep can you go with this method? So usually the depth that you can reach in the subsurface with your image is about, you take the full length of your survey and divide it by 5. And so, for example, in the pecan orchard, we set up a line that was 291 meters. And then so you divide that by 5, and you're getting roughly like 50 to 60 meters in depth from that. And there's different types of arrays or different types of configurations that can be set up. I won't talk too much about those today, but they're good for different applications. So there's considerations that need to be taken into account on how you set up your resistivity survey. And then basically, so each measurement is taken with 4 electrodes. Even if you have 112 set up, it'll usually light up 4 at a time, or be using 4 at a time for a measurement. So 2 of those will induce a current in the ground, and then the other 2 will measure the voltage. And so you'll be building up a picture of how well that electricity was conducted through the earth. And so these figures also kind of talk about just the basics of how the instrument works. This is when I mentioned different types of arrays. This is different types of arrays. Basically, you have 4 electrodes. They're set up in different configurations. And so some of you may have worked with this kind of data. You might know, you might set up a Venner array or a Schlumberger array. They're for different types of applications. But I just kind of in general today wanted to mention that these different types of arrays exist, and they're used for different types of imaging problems. But when you set up a survey, usually you'll have a number of electrodes, and then your control module or your computer connected to the control module will tell it to take measurements with so induce currents with different electrodes, and then measure the voltage with other pairs of electrodes. And so it will kind of run a program. And when we run these with our system, the AGI SuperSting, we're usually, it might take even 4 hours to run the program and to collect the data. But then we would get some data, and then we would invert the data for the subsurface conductivity or resistivity, and we might get a picture that looks sort of like this. So it can be useful for a variety of different things. I listed some of them on the left. This particular application on the right is for kind of groundwater and shallow subsurface soil structure. And so you can see the top is just the resistivity data. So the high resistivity here is the purples and reds, and the low resistivity is the blues. So you think about, you might expect, so the blues, low resistivity, high conductivity, water should be relatively high conductivity. So the blues would indicate potentially water, and even the darkest blues or the lowest resistivities could be salty. But I think in this situation, it's not that low. But so, for example, you would see this data at the top, and then there's some interpretation shown in this picture on the bottom. Basically, they interpreted some sand, sandy gravels, clay layers. The clay is, for example, here, this kind of pattern is the clay. You can see it over here. And so that's interpretations based on the measurement of the subsurface resistivity or conductivity. They're just inverses of each other. And then so coming back to the pecan orchard and Jose Cabral's project, this is the data collected in the 5R Ranch in Tornillo, and it's sort of parallel to a line of pecan trees, like it's along the, and so there's, unfortunately I didn't put little symbols on here, but there's like the pecan trees at something like 10-meter increments along this line. But you can see, so here the low resistivities again are in blue. So you might think about the blues, values of around, this conductivity here. So the fresh water, you look for resistivity. So maybe from 5 to 100, you might expect could be fresh water. Salt water might be more like 1s. So these 1s might be, salt water, if it's present here, might look like that. And we know from wells drilled in this area, so like the ground truthing from wells, that the water, you hit water at about 12 feet, so like 4 meters. And so this blue unit might be the indication of sort of the top of the water in this area. And we think that so the areas where you see it's a little bit more green, and maybe we've seen it in some other data from the pecan orchards, but you can see the root uptake from the pecan trees kind of impacting like a zone a couple of meters below the pecan trees as well. And then some of the, you can see some other sort of structure in terms of the soil units. And in this pecan orchard, there is some clay as well. Clay here, this, would be, you notice it's overlapping with fresh water, right? So you can see where it could be confusing, and you need other data to help with the interpretation, or, you might come up with a couple of possible interpretations. But it can be useful for getting an additional picture of the subsurface structure. Okay. So that's electrical resistivity, and an example of a sort of ongoing project looking at that in the pecan orchards. The next method I wanted to talk about is gravity. And so gravity, or sometimes called microgravity, is often used to see small scale changes in water systems. So for example, we see this actually in Juarez in Mexico with some time-lapse data of gravity through time. You can see that the amount of pumping and the amount that the Juarez aquifer is known to have dropped is about the same as you'd expect from that amount of mass of water to be removed from the system. When you look at the gravity data, like through time, there's gravity data collected by UACJ and Juarez like every 10 years for about the last 30 years. So you can see that in the gravity data, what is also known from the well data in that area, that the aquifer has been drawn down. So one of my PhD students, Marianne Garcia, she actually just started last year. So she's just started working on this, but we have you can see all these little dots are gravity measurements that have been collected in the Hueco Bolson. So here's El Paso and Juarez. There's the Rio Grande, Mexico and US. And so you can see a lot of these lines cross the international border. I'm saying lines because these are the areas that the yellow lines here are focused on sort of focus profiles that she's going to model for the gravity. And so we have these gravity measurements on both sides of the border, and we're collaborating with UACJ on this project. They collected a lot of the data in Mexico. And so what this can do, what we're looking at here is gravity allows us to identify density contrasts in the subsurface. And so we're interested in looking at the sort of the structure of the basin from the gravity in this area. So where do we have less dense sedimentary rocks, more dense basement rocks? We can kind of map out like a rough idea of the structure, as well as where there may be faults from gravity data, even if you don't see a signature of the fault at the surface. If there's a fault cutting units in the subsurface, you might see that in the gravity data. And so you could also, like I mentioned earlier, for Juarez, you might be able to identify changes in groundwater if you have data on gravity through time. And so I mentioned, I think before, that gravity, we're basically just measuring the gravitational attraction of kind of everything in the area around where you're working, but you do some corrections so that you get a good relative gravity that can then be used to model the density in the local area. And so here's an example of some previous work by Avila and Dozer at UTEP about 10 years ago now. And so this is basically an example. This is Miriam also wants to do something similar for her PhD project. But they had data, and this is now the northern part of the Waco Basin. You can see the border with New Mexico here, Texas and Mexico border. So the color here is the gravity anomaly. But they're looking at, so for example, B to B prime, A to A prime is in southern New Mexico. But like if we look at B to B prime, it's shown here at the bottom. So we have this gravity data, and then they've used that gravity data to model a subsurface structure that fits the gravity data. And so you can see here the observed gravity points are shown in black, and then the black line is the calculated gravity from this specific model that they published in the paper. And so we're trying to come up with a model for the, you could call it maybe the mid to lower Waco Bolson crossing the border with Mexico that would look something like this, that crosses over the Rio Grande in that area. So based on the data that I showed you earlier, she's working currently on kind of creating a density model that could then be translated into a lithologic model of the southern Waco Basin. And so in addition to lithology, the density can also be impacted by pore space and fractures and the density of fluid in the pore space. And so those are other things that are taken into account when doing this type of modeling. And again, like I love geophysics, but I also love geology and hydrology. And I feel like the more data you have, the better. So you always want to bring in all the data you have to interpret the results, whether you're looking at gravity data or seismic data or any kind of other type of data. And so a little bit more background on the gravity method. You may be familiar with the universal law of gravitation is shown here. It's this basic idea of the force of gravity related to mass. You know, it comes from masses, right? So you may have seen it in, it's talked about for planetary bodies, but it also applies to any masses. So the mass of within the Earth or of people walking around on the Earth. But you get some force of gravity for every mass. And it also depends on the distance between the masses. The R is the distance. And so in geophysics, we usually, what is measured is small scale changes in the gravitational field that are based on the density of materials in the subsurface. So I won't go into it today, but there's a number of corrections that you do to the data after you measure it to sort of account for the fact that there's tidal signature is seen in gravity data, and there's other types of things that are seen in gravity data. You get an effect of elevation as well. All of that is removed if we just want to look at what's in the subsurface and the densities of that. And so when we are looking, the data I'll show you has already been corrected for those things. So basically we're looking at acceleration due to gravity in different areas, like slight differences in that based on the densities. And we often in geophysics use milligauss or even microgauss to look at tiny scale variations that could be based on an area where you have changes in the groundwater level but the same geology, or areas where you have like an ore body that's extremely dense and you're trying to find that ore body. And this is mostly just for reference. I just wanted to mention, so you can look up the density, bulk density of, these are showing you sedimentary rocks. So bulk densities, for example, might be, these are for different units in different areas, but you might see 2.5, 2.7 grams per cubic centimeter for different sedimentary rocks, these kinds of numbers. And then you can see here for igneous rocks and metamorphic rocks, again, like ranges of densities. Again, there's overlap between different rock types, so it can be sometimes difficult to tell between certain types of rocks. But for example, if you have a really dense ore body, that would be very distinctive, or basement rock compared to sedimentary basin rock would also be different. If you have igneous basement, for example, in the Hueco Bolson, and there's many parts that have the sort of granite or syenite basement. And so if you see changes in the density, you might be able to say that it's sort of like offsets in the basin from a fault, for example, in the basement. And then this is the instrument that's used to take a gravity measurement, or one of the type of gravity meters. This is a Lacoste-Romberg gravity meter that we have at UTEP, but there's other types. And it's basically what it looks like inside. It's using a mass on a beam attached to a type of spring, and it basically can measure very fine scale variations in the Earth's gravitational field with that type of instrument. It's a very finicky, like you have to take very good care of it if you take it to the field. And then this would be, for example, this is the map that Marianne is putting together for the Southern Hueco Bolson. And I apologize, she hasn't put the the international border kind of runs through here, the Rio Grande. And then you saw that on the previous map, but this is showing you the Bouguer anomaly. So it's the gravity anomalies, the changes in gravity. So you have the blues are the lower gravities you see towards the Rio Grande, and it's sort of the center part of this area near the border. And then they become higher as you move. The gravities are higher as you move away from that, from the international border, from the Rio Grande River. And the highest gravities in this area are on the Mexico side, and these would be controlled by the structures in the subsurface. So she's going to use these data to model the subsurface structure, like you saw from the Avila study in 2016. Okay. And then my final example of a data type, another type of geophysical data, is seismic imaging. This is another project from one of my PhD students, Michel Luna, and he's working in the southern Jornada del Muerte Basin in the Jornada Experimental Range, which is shown. So here's like white sands, if you're familiar with white sands in New Mexico, Las Cruces, El Paso, Juarez, the Sacramento Mountains. The San Andres Mountains is the mountain range just west of white sands. And so it's northeast of Las Cruces. And we're looking at this little yellow line inside the little blue box, which is zoomed in this area. And so you can see that, so this is the Piedmont slope of the San Andres Mountains. And it's an area where there's been several faults previously mapped running approximately north-south through this area. So we did this seismic line hoping to, and it's an area where there's a eddy flux covariance tower, there's a ongoing hydrogeology study, there's a well drilled on the playa, sort of over here-ish. It's a little bit outside of the box, but so there's a number of different types of work being done here, and so my group in a couple of years ago decided to collect some seismic data as well and try to help the other groups with figuring out where are the faults. They've also done radar. I didn't talk about radar today, but radar surveys looking at shallow caliche layers in this area, because the caliche is a more impermeable layer and can impact the water flow. So a lot of these types of studies are looking at water flow coming off this mountain range, and this is the Piedmont slope. So looking at where you might be getting water going into the ground along faults or fractures, and whether or not it can actually get in there with the clay layer, impermeable layers, things like that. The method that I'll talk about is seismic reflection. It's kind of like echolocation in that you're making a sound and listening for the echo back, and then you're getting the speed that wave traveled, which can tell you something about the material that it went through. And So the basic things you're looking for usually are how long did it take for your echo to come back, tells you the velocity, which is the composition or layer thickness. And then you can also sometimes look at the character of the reflections to tell something about rock properties or the presence of fluids as well. And I wanted to mention so this is showing you this is from a scientific paper about echolocation in dolphins. And you could see this dolphin looking at the diver, trying to map out who is this, what is this? And it's the dolphin, as far as we know, is getting a pretty fuzzy image of what's going on with the diver. But if you use computer processing, you can sort of enhance this computer enhanced version of what the dolphin saw as shown here, and you can maybe see a little bit more of an actual outline of a person. And so I wanted to show this just as an example of, so this is similar to, there's certain types of computer processing and ways we can kind of enhance the signal with seismic imaging as well. And the oil industry does this all the time, as well as other types of industries using seismic reflection data. It's used for geothermal characterization, looking at reservoirs, a variety of different applications. But often there's an element of sort of tuning your image so that you can hopefully get a more clear picture of what's going on. And so in seismic reflection and also in refraction, you can sort of see or image layers beneath the surface. And the seismic waves are basically waves of energy that travel through the Earth's surface. And so there's an example of how a survey might be, source might happen as a sledgehammer on a metal plate, measured with geophones. A little orange dot there is a geophone. And then this is an example. This survey was actually taken with a hammer in Yellowstone across the Old Faithful geyser. This was a model put together by an undergrad working in the summer, Juan Pablo Esparza. And so he worked on getting a velocity model beneath this area. There was a line of geophones and then hammer strikes all along that line. We actually had 10 hammers at each place to be able to increase the signal to noise on the data. So you kind of stack the data by doing multiple hammers. But we got a reasonable image down to, you can see here, 2235, 2175. So we're getting down like 50 meters or so, 40 to 50 meters. Over here, it's a little less. But we can see, so we see this, in particular, we see this sort of low velocity zone, which this is kind of overlain on a previous study where they were suggesting the hydrothermal reservoir for Old Faithful was off to one side. That was from a different type of seismic data. And so it was interesting that we were sort of picking up the edge of probably this hydrothermal reservoir is what's causing the lower velocity in that area. So I just wanted to kind of use that as an illustration of the method. And so in that was an example of seismic refraction. So we were looking at refracted waves in the subsurface, how fast are they going, and building up a velocity model. In seismic reflection, you're looking more at those sort of reflected waves coming back. But you can see examples here. You have a source, you have a receiver, you have reflected waves, you have a head wave as a type of refraction. Then you end up with your sort of seismic wiggle for each geophone of recorded ground motion. So again, like your source, your receiver, your geophone, it's like you're making a noise, you're listening for it, and then you're working out what the signal means. So you get this sort of seismic wiggle that is the same as you get for earthquakes, but this is for our specific man-made source. And you can record with a source or from the natural background environment, all kinds of different waves. These are showing you how P waves, compressional waves, shear waves, S waves, and surface waves propagate. And how surface waves, the little house is telling you like the most damaging in an earthquake is the surface wave. That's why the little house falls down. And the S wave is generally higher amplitude than the P wave, so it causes more damage. And the directionality of like how the wave propagates, you can see a P wave, it's sort of compressional moving across. The S wave has particles moving up and down. So that's part of what causes more damage to homes, for example, in an earthquake. But when we use seismic for shallow near surface imaging with hammer sources or small explosions or vibrator trucks or weight drop sources, there's a lot of, or even they have a Betsy gun seismic source we use sometimes. We have one of them at UTEP, and there's a couple more you can borrow from EarthScope. But it's basically like firing an 8-gauge cartridge in a hole in the ground. Usually we drill down 2 feet, fire it there. It creates seismic waves. And usually, so you might ask, like, how deep can you go with this method? And it really depends on the size of the source, the subsurface structure. And but generally, sort of a rule of thumb is typically the depth image is about 1/3 of the largest source receiver distance. And so if you have a source that can go 2 kilometers, or let's say 3 kilometers to make it easiest, you would be imaging down 1 kilometer. So the survey I'll show you in the Jornada del Muerte Basin, we imaged like 3 kilometers in the surface and got a depth penetration of about 1 kilometer with our data. This is for refraction. And it's often kind of similar for reflection as long as your source goes far enough. So we actually had issues when we used the 8-gauge seismic gun. It didn't work as well as the weight drop source that we used. That was higher energy. So you have to have a source that will also be able to go down 1 kilometer and come back up. And then these are some typical wave velocities for P waves shown in red and S waves shown in blue for different materials. So you can see how you can, again, like with some of the other methods, there might be overlap, which you have to be careful about, but you can map out some of the differences between different types of materials in the subsurface. So even whether you have dry sand, wet sand, clay, there's also resolution limits on thin layers, for example. So if you have a very thin layer, like caliche can be very thin, say it's even if it's a foot, even half a foot, you probably won't see that with this method unless you'd have to do a very sort of tuned specific survey to even hope to see that. But I think like you may not be able to see it at all at that level. Usually it's used for a little bit larger scale imaging. You might need something that's say 5 feet or a couple of meters thick to be able to see it in a shallow survey. And here's just a list of some different uses for seismic refraction and reflection. Here's a study by Brady Flinsham and others in 2018, where they're looking specifically at aquifers. So they're seeing the unsaturated part of the aquifer, the sort of weathered rock, which holds more of the water, and then this fresh bedrock. But they've identified kind of these different sections of the system using seismic data, that some of which is shown here. They got like depth to bedrock, water capacity they were able to calculate. And all of this is, there's based on some assumptions about how you're interpreting wave velocities. But there, you would always want to test, you come up with a model, then you check it against other types of data and put it in the framework of all the data that you have. So, and then sometimes it can be, often it can be quite useful for getting a different way of looking at the subsurface. And so here's some pictures from the reflection imaging I mentioned in Jornada del Muerte on that Piedmont slope, where we're looking for a big normal, relatively big normal fault that we think is there from other work that's been done in the area, including there's seismic data a couple of kilometers to the south. And so we're kind of looking for where that fault extends to the north of that area. We used both, this is a weight drop source that we used for this project. We also used a seismic gun source, and we also did some smaller scale projects with a sledgehammer. This was a class that I taught last year with students doing the seismic source. And then we recorded these either on, you can see here, cable geophones or on standalone. This is a 3-component, what's often called like a seismic node, like just a small geophone. You can listen with that. The battery lasts about a month, and it's great for different types of seismic studies. We have 110 of them at UTEP for different projects. Okay. And so some of the results from that. So this was the seismic line. There's a couple of wells that are south of the area. So you can see here the units identified in the wells as sort of, again, ground truthing. Like we're thinking about our interpretations. We want to use all the data, right? And so you can see there's shallow quaternary material at the surface, and there's Paleozoic, mostly limestones, and then volcanic rocks. And so this is the seismic data is in the background, and then you can see these wells that are not right on the line, but they're like 1.5 kilometers away or so, maybe between 1 kilometer and a half. And in these data, we see actually, I'll just put it next one. Or actually, I'll mention just briefly. So there was a previous study done by Diane Dozer and Mark Baker that was published in 2021 in this same area. The red box is the area where we collected these data. And they looked at magnetic and gravity data, and were able to put together a subsurface model suggesting this Western Boundary Fault Zone 2, WBFZ2, may be kind of towards the middle of the seismic line. This is the seismic area. And so we were looking for that. And this is a very preliminary interpretation. Michel is still working on his interpretations, but I just wanted to kind of highlight, we think that this shallow part, you see sort of the semi-horizontal layer. We think this is the shallow sedimentary layer on the top of the Piedmont. And then this may be the normal fault. You can see a change from more coherent reflections over here to less coherent over here that we think might be consistent with a shift from the Paleozoic sedimentary rocks like limestone to the igneous rock over on this side. And he has another interpretation. Again, I mentioned we're working on different interpretations where the igneous rock it looks like in the well data too, like there may be a small like tongue of the igneous rock or a little bit of the igneous rock that is narrow and kind of crosses over the fault. And that might be what's going on here, but we're still working on the interpretation. But the basic idea is that we're working on identifying faults, fault geometries, trying to get different types of information about the subsurface to understand the water flow and where there might be fractured rock. It's also used a lot for earthquake studies. You might look at, how large is the fault in the subsurface? Is it look coherent? Like you could possibly get a larger earthquake on it or not, for example, for active faults. And then in the last just few minutes, I wanted to mention, so I sort of titled the last section, Future Opportunities and Challenges. And of course, there's many, many of those. But I thought, since I've heard a lot of hype in El Paso recently about geothermal energy, that I would mention a little bit about what I've heard about geothermal energy in El Paso and then what different folks are working on. But there's been some discussion of geothermal as a important source of energy, particularly in El Paso, where it's in the Rio Grande Rift, which has relatively high heat flow. You have a lot of people there, a lot of energy needs. You also have a great opportunity for solar. So you could possibly have solar during the day when it's possible. And then, geothermal at night is something I've heard people talk about. But there's a lot of challenges. I'm a little bit skeptical, but I think it's also important to think about and explore. So I've been trying to get in. I wrote a grant last year to Department of Energy to do some exploratory work, collecting more data for geothermal, basically looking at fracture zones and fluids in the Hueco Bolson. And then I'm working on another proposal now that would involve exploratory drilling as well, that I mentioned to a few people earlier. But also for Department of Energy, they have a big call for next generation geothermal energy, exploratory drilling, as well as producing energy. And again, this is just some of the, these slides are actually from my colleague, Jim Kubicki, like some of the news media coverage of, West Texas region holds promise for geothermal. And this, you could probably find the same headline 40 years ago. I don't know. I know there's been different phases of exploration and looking at this. And I think some of the excitement recently that I've heard at least ties in with the advances in drilling technology and advances in the oil fields for directional drilling, for fracking, and whether or not that opens up more unconventional geothermal. So if we look at kind of what is geothermal, how is it used? So it basically leverages having areas with higher temperature in the subsurface, and so that geothermal gradient usually averages about 25 to 30 degrees Celsius per kilometer in the upper crust for the top 10 kilometers. And in an area that could be explored for traditional geothermal, you often need a geothermal double or triple that. So you'd need like particularly hot water, like the geysers in California, for example, has been a successful geothermal field. Have a friend who used to work there. And but it's, that's generally not quite the level of geothermal gradient that's been seen in West Texas and in New Mexico. And so the question is, is there enough heat that you could, or enough even heat in drier areas where you could use that for more unconventional type geothermal, like hot, dry rock geothermal, where you would pump water into deeper depths where you have hot rocks, heat up the water, then bring that water back to the surface, for example. And you need fluid flow pathways. So you may need to, there's discussion of, you might need to frack to create fluid flow pathways at that level. So in the Rio Grande Rift, which is shown here, you can see El Paso. And then, there's obviously a lot of hot springs. It's an active rift system. And so in terms of the geothermal gradient, these are the temperatures at 6.5 kilometers from a relatively sparse data set from SMU. I'll show you more detail of the El Paso data in a minute, but I also wanted to highlight this 1981 PhD thesis for West Texas, where they're looking at, they see some like little pockets of high geothermal gradients in West Texas that I'm sure many of you are aware of. I know there's like hot wells. There's other high geothermal gradients where you might see hot water in one place and you drill a little ways away and it's not hot anymore. So that's one of the challenges in this area. And then this is the more detail of I plotted the SMU database on, so this is showing you the depth of the wells. This is the El Paso area. So there's southern New Mexico, El Paso, and this only goes as far as Alabama, I apologize. But there's data in other parts of Texas, obviously, too. But just wanted to highlight, there's only a couple of deeper wells. This is the well depth. And these are the bottom hole temperatures after allowing the hole to the bottom hole equilibrium temperature. And so you can see some of the areas where you have the deeper wells that are hotter, looking at 100 to 150 degrees Celsius. And then up in the McGregor range, there were a few even somewhat shallower wells that got pretty hot. And I know some of you are probably drilled those wells and are more familiar with it than I am. But I just kind of wanted to highlight some of the trends. So again, you see some of these hotter geothermal gradients and then some more normal geothermal gradients. And so there's sort of just highlighting like opportunities and challenges, right? So I think there's if it's going to be possible, then it probably needs to be more work done figuring out why, where are these specific hotter areas and are those places where you could potentially do this? And obviously it's also interesting scientifically to understand these systems and where the water's coming from, how it's flowing, and it all sort of crosses into aquifers and hydrology systems as well. Okay, and this is my last slide. So you're welcome to contact me. This is my dog Chase doing a seismic survey in the Indio Mountains south of Van Horn. And then I also recently have been doing work on hydrologic systems and glacial outburst flooding in the Himalaya. And we were talking about remote sites. And this is we were like a 5 days walk from the nearest town. And so but it's also really interesting. I think I would just put it here because it's interesting. We're using geophysics to understand these very high mountain hydrogeologic systems in the Himalaya. And it's just fascinating to me, both in West Texas, as well as in the Himalaya and other parts of the world, just the differences in the systems and how you kind of trying to understand these things. And, people have the same issues there, trying to get fresh water for their towns and villages and homes. And just it's like a 5 days walk from the nearest grocery store. So thank you very much.
You said that I remember when you were talking about resistivity, the water table is 4 meters below ground level in the pine orchards in California. You know, that's really shallow, and I think the river is dry there. So is that just a function of continued application of flooding?
Yes. So it is very near the central channel of the Rio Grande in that area. Like there's two pecan orchards, two different properties where we've collected quite a bit of resistivity data, and there's wells as well. But yeah, it's the continued irrigation, and you can see of course, right after they do flood irrigation, so a couple of my colleagues, especially Hugo Gutierrez, has been working on how that, how quickly does the water get down to the typical level that they see of the 12 feet. And they've actually done some resistivity studies. I haven't seen like the different, they've been looking at doing the resistivity. You can't do it right after they flood for sort of obvious reasons when the water is there, but when it's still muddy, I think they collected it once, trying to see if they can actually see the water like going down from surface level to even to the 12 feet. And so it is, yeah, to answer your question, it is most likely because they're basically flooding pretty regularly in the fields. And so it stays at about that level when.
Is there anybody, I know there's a lot of work being taught directly in the orchards. Is there any work adjacent to the orchards to do any comparative study?
There is some work adjacent to the orchards, or in the sense that, I mean, trying to think of where there's been some work done in other parts of Tornillo. It's not kind of right next to the orchard, but there's been work done like in some areas where they irrigate differently. I know they've looked at that. I don't actually know if they've specifically done resistivity on an adjacent field, for example, which might be quite interesting to see the difference. But I know the wells that are off their site, because there are some other wells that I've seen data for, and the water is deeper. It's not at 12 feet, but it's also getting farther. Those are also farther from the central river channel. So it's a little hard to tell what are the different factors, but I think it is the irrigation that keeps it there. Oh, I didn't, but I've worked with there's airborne electromagnetic data, beautiful data collected over a lot of the Trans-Pecos recently by the Earth MRI. Yeah, so I don't think it extended that far east. At least there was a Earth MRI data that was published in 2021 online by USGS. And that's the data I've been working on with a postdoc recently. We've been mostly looking at the Cornudas area and the Sierra Blanca area, which but I think that data set didn't come to the sense like that far east. But I know they were flying more. And I know in New Mexico, they just recently in the last year, the helicopters have been out flying more airborne magnetics. So they might be having, I'm not sure if they have been here yet. Yeah, it's a great question. I'm not sure specifically for that area. But I know in like across a lot of it goes as far, it definitely is covering like Sierra Blanca, Van Horn, but then I think the data I've looked at kind of, we didn't go any further east from there. So I'm not sure what's available further east, but there may be even older surveys, even if it's not the newer Earth MRI data. But it's very cool data, the magnetic data.
Thank you so much.
Thank you.